Hello, my name is Cody Creel, and this is my cosmology assessment for AST322. I used the Planck CMB simulator to create a hypothetical universe by adjusting the densities of baryons, dark matter, and dark energy. I kept the Hubble constant, the cosmic microwave background temperature, and radiation density fixed at these benchmark values. A Hubble constant today of 70 kilometers per second per megaparsec, a cosmic microwave background temperature today of 2.73 kelvins, and a radiation density today of 9 times 10 to the negative fifth. And my chosen parameters were a baryon density of zero point 0.2, a dark matter density of 0.375, and a dark energy density of zero point 0.4. These differ from the benchmark by more than 20%, and the simulator reports a universe similarity of 63%. At an age of 11.6 billion years and a fundamental scale at the multipole moment in the power spectrum L and an open geometry. And here are the CMB maps from the simulator. On the top right map shows the benchmark universe, and the bottom left map shows my simulated universe. And you can see that the simulated map has a smaller angular features and brighter contrast. This reflects the open geometry and increased baryon fraction. Open geometry increases the angular diameter distance to recombination, which projects the sound horizon onto a smaller angle. And that's why the features look tighter and more intense. And this is the angular power spectral comparison. In my model, the first acoustic peak shifts to a higher multipole moment in the power spectrum, or L, from about 220 in the benchmark to 264 in the model. This shift indicates that the acoustic features subtend a smaller angle on the sky. The increased baryon fraction also enhances the odd number peaks, especially the first one, due to the stronger compression in the photon baryon fluid. Open geometry reduces the angular diameter distance to last scattering, shifting the angular scale of the acoustic peak so the same physical scale subtends a smaller angle on the sky, or the peaks move to a higher L. And this matches the simulator's fundamental scale at L of 264 with a smaller angular scale. And high baryon fraction increases odd compression peak heights relative to even rarefaction peaks and increases acoustic contrast, so the map looks brighter in spots. And the net effect on the map and power spectrum shows peaks shifted to higher L and changed relative heights. The simulator's notes are qualitatively explained by these parameter changes. So let's break down why these changes happen. Open geometry decreases the angular diameter distance, so the same physical sound horizon appears smaller on the sky. That pushes the peaks to higher L. Meanwhile, baryon loading increases the inertia of the photon baryon fluid, which boosts compression peaks, or the odd number ones. So geometry sets the peak positions, and baryons set the relative heights. And so now let's look at some early universe properties. The photon to baryon to photon ratio, or eta, is the number of baryons per CMB photon. It affects Big Bang nucleosynthesis and recombination. I computed eta using the physical baryon density, which is the actual mass density of baryons in the simulated universe, scaled by the square of the Hubble parameter. With a 0.7 Hubble parameter, I acquired a physical baryon density of 0.098. Scaling from the benchmark baryon to photon ratio of around 6 times 10 to the negative 10, I acquired a baryon to photon ratio for my model of around 2.67 times 10 to the negative 9. So my universe has about 4.5 times more baryons per photon than the benchmark. Matter radiation equality occurs when matter density is equal to radiation density. So using the formula 1 plus redshift of matter radiation equality equals total matter density over radiation density, I found a redshift of matter radiation equality of approximately 6,389 and a scale factor at equality of approximately 1.565 times 10 to the negative 4. Compared to the benchmark redshift of matter radiation equality of about 3,500, my universe reaches matter domination much earlier due to higher matter density. And recombination marks when free electrons combine with protons and photons decouple. It depends weakly on the baryon to photon ratio, with eta being approximately 4.5 times the benchmark. I estimate redshift of recombination of approximately 1200. When I plug this into the formula for the temperature at recombination, or T naught times 1 plus redshift of recombination, I get approximately 3,276 kelvins. So recombination happens slightly earlier and at a slightly higher temperature than in the benchmark. And dark energy begins to dominate the universe's expansion when its energy density equals that of matter. So using the relation 1 plus redshift when dark energy equals matter equals dark energy density over total matter density, and substituting my model's values for dark energy density of 0.4 and total matter density of 0.575, I find approximately 0.6957. And taking the cube root gives 1 plus redshift when dark energy equals matter of approximately 0.887. This corresponds to a redshift when dark energy equals matter of approximately negative 0.113, meaning the transition to dark energy domination will occur in the future. The associated scale factor when dark energy equals matter equals 1 over 1 plus z lambda of approximately 1.127. So while my universe is still matter dominated today, it will eventually enter a phase of accelerated expansion driven by dark energy. So here's the summary of the early universe quantities. I got a baryon to photon ratio of around 2.67 times 10 to the negative 9, which was 4.5 times the benchmark. A redshift of recombination of around 1,200. A temperature at recombination of around 3,276 kelvins. A redshift of matter radiation equality of around 6,389. A scale factor at equality of around 1.565 times 10 to the negative 4. A redshift when dark energy equals matter of around negative 0.113. A scale factor when dark energy equals matter of approximately 1.127. And these values show how my parameter choices shift key cosmic transitions. I chose a redshift of z equals 10 to analyze the expansion during matter domination. At this redshift, the scale factor equals 1 over 1 plus z, and I got 0.09091. Using the Friedmann equation, I computed a radiation density of approximately 1.318 and a total matter density of around 764.825, a curvature parameter of around 3.014, and a dark energy density of 0.4. Total Hubble parameters squared was approximately 769.557, and so the expansion rate was approximately 1,940 kilometers per second per megaparsec. And the critical density at a redshift of 10 is about 770 times higher than today. Matter dominates with 99.4% of the energy budget. Curvature contributes only 0.4%, so it's dynamically negligible. Even though the universe is open today, it behaves like a flat matter-dominated universe at high redshift. And the curvature radius today is about 27,113 megaparsecs at a redshift of 10. Curvature radius at a given time equals curvature radius today times the scale factor, and that is approximately 2,465 megaparsecs. The Hubble radius is approximately the speed of light over the Hubble parameter at redshift, and is approximately 154 megaparsecs. So curvature radius at a given time is greater than the Hubble radius, and the curvature scale is much larger than the causal horizon, confirming that curvature effects are small at this epoch. So to summarize, the Hubble parameter at redshift is approximately 1,940 kilometers per second per megaparsec, with a matter fraction of 99.4% and a curvature fraction of 0.4%. The curvature radius at a given time is approximately 2,465 megaparsecs, and the Hubble radius is approximately 154 megaparsecs. So the universe is decelerating at a redshift of z as expected during matter domination. Because my dark energy density is 0.4, dark energy will eventually dominate. At a scale factor of 1.127, the universe will transition to accelerated expansion. Despite being open, the positive cosmological constant lambda prevents recollapse. The long-term fate is eternal acceleration approaching the de Sitter-like state. Because dark energy density today of 0.4 is positive and non-zero, lambda will eventually dominate. And we found a quality at a scale of 1.127. So the expansion will accelerate in the future. The long-term fate is eternal accelerated expansion, or dark energy dominated, and it will not recollapse, even though the geometry is open. A future cosmologist observing the only late-time dynamics would infer a growing importance of cosmological constant that represents dark energy lambda and eventual de Sitter-like expansion. And comparing to the model given in the packet, my model point for my universe, the total matter density of 0.575 and dark energy density of 0.4 lies below the flat line and outside the observational contours, centered near 0.3 and 0.7. So my model is observationally disfavored. It doesn't match current supernova, baryon acoustic oscillations, and cosmic microwave background constraints. So to wrap up, large baryon density boosts odd acoustic peaks and increases eta and recombination temperature. And large total matter density shifts matter radiation equality to higher Z and keeps the universe matter dominated today. Open geometry shifts acoustic peaks to a higher L, producing smaller angular scale CMB spots. And my model disagrees with observational data, but offers insight into how cosmological parameters shape the universe's evolution. The fate is eventual dark energy domination and eternal accelerated expansion. So thanks for watching my presentation. I really enjoyed exploring how small changes in cosmological parameters can lead to dramatically different universes, and I'm happy to answer any questions or discuss this further. Thank you.